What?
Okay,
Oh,
I'm
okay.
recording now. Thanks.
Perfect. So I'm going to share it again. So you can see my screen?
No.
Nope.
No.
Not anymore. Okay. It's,
One thing I like to ask about is when
Yeah.
meetings are virtual around the world, who is in the least convenient time zone for the meeting?
right now, I think it's you.
I think it could be me.
Yes.
And
This
even
time,
that's
this is
not
what
too
I
bad.
wanted to say this time.
What's the time?
It's 11 p.m. for me,
It's 11 p.m.
Oh, 11 p.m. Oh,
but that's not too bad. I had a meeting.
So
late.
it's still okay, I think. It's still okay.
Yeah, it's not too bad.
So that's why you were among the first who were going to give the talk.
I appreciate it.
It's good to say it. So it's 8 a.m. in France, in
Mm.
Paris. So we are a couple of us here, maybe even more. So it's in China right now. I think it's 2 p.m. if I'm not wrong, but I think it depends a little bit. So I think the time zone. It's kind of worldwide, but I think you're the one which is maybe the most inconvenient. I don't know.
Good.
Yeah.
I win.
Next, just to a small parenthesis. So next week, I'm going to give a talk at ACII in Japan, who's taking place in Japan, and they proposed me like some slots at 2 a.m. in the morning. So I said no, I declined. So now I have one at 6:45 in the morning. But it's still at the limit, so I'm in the balance of like recording my presentation, which is possible, or giving it live. But it's still like I didn't decide it yet. So yeah, okay. So thank you all for being here to this workshop. So it's the workshop on human behavior understanding, having an eye inside and outside the car for better accident prediction. So this is part of the 25th International Conference on Intelligent Transportation Systems. And as we just said, so we are all around the world, and so the time zone, it's not convenient for everyone, but I would like to thank all of you for being here. And I hope that maybe next year is going to be a face-to-face meeting, because this conference is great and I really enjoyed every time I attended it. Okay, so I'm going to go next. So this workshop, so there are several organizers. So there we have 5. So myself, I'm Professor Adriana Tapus from ENSTA Paris in the Autonomous System and Robotics Lab. And Taegong Shangguan, so he's my PhD student. Professor Xuyang Gilan and Meng Yuan Ding, sorry for maybe not pronouncing it well, your names, from Institute of Artificial Intelligence and Robotics at Xianjiatong University in China, and Professor Neng Chao Liu from the Intelligent Transportation System Research Center at Wuhan University of Technology.
I'm sorry,
Okay.
Adriana, do you want to maybe put your slide deck into presentation mode? Because we're still only seeing the intro slide.
Oh. But I put that. Okay, so let me share it again. Sorry. Yeah.
It's all right.
Thank you for saying. So did you see this?
It's like we're looking at the, the open view of the presentation, not when it's in presentation mode. Oh, there
yes.
we go.
Yes, right. Yeah.
Well, that's better. It's still in open mode, but at least we're on the right slide.
But now you still cannot see the full slide.
Yes, we can't see the full screen. It's in the PowerPoint view.
You can play the PowerPoint.
Yeah,
I mean, it was okay that way.
it's, we are using it so like for 3 years almost right now, Zoom, and there are always some small
That's okay. I tried to give a live technology demo of a prototype today, and it went about how usual you would expect live demos of prototypes to go.
yeah, it's okay, let's try again, and if not, so I will put it in
Yeah, that's okay.
full.
It's
Can you
still
see
in
it
the
now, Paul?
PowerPoint.
Still not seeing the full PowerPoint?
Yes. It's in
I-
the-
No, but as long
Maybe-
as you click through the slides, we can see
Yes,
them.
yes.
Is it working? Okay, I'm sorry, I'm going to do it like that. That's fine. As usual, there are some. Okay, so as I said it earlier, so these are the 5 organizers. I'm not going to tell it one more time. Okay, so let's start with the context. So where did this come? Where did we come with this idea? And so there is a lot of work that it's done in autonomous system, but we're still far away, I think, from having all the cars on the street to be autonomous. So we are not there yet. And I think that truly autonomous vehicles are a little bit behind the optimistic rollout schedules predicted a few years ago. So humans, we all know, so they are like inside and outside the car. So I think they are really playing a crucial role in all the driving scenarios. So both, as I said, inside and outside the car. Inside the car, because the drivers have to focus on the road, on the driving behavior, the environment, and outside the car, of course, so there are like a lot of factors so that influence so the driving, so the emotional state, the time of the day, the cognitive load, and so on. So the driver's risky driving behaviors are really responsible, and we're going to see that today during the presentations, for most car accidents. And so that's why we need to understand human behaviors and find some of the interpretation of all these behaviors in order to be able to prevent or predict some of the accidents. Of course, we're not going to be able to predict all the accidents. That would not be possible. But that's inside the car. But we also have an eye outside the car in the vehicle, because there are like pedestrian and other things that are happening in traffic and everything that is happening outside the car. That's why we really, I think, in my opinion, we really need to have these simultaneously have an eye inside and outside the car in order to achieve a trusted, intelligent system that is able to keep human beings away from traffic accident threats. So we all know that also, for example, it's very difficult for machines to view the world the same way we do as humans and assess of what is happening like outside, see what is coming and making all these decisions. So the difficulty, I think it's coming not necessarily only from the sensors or anything with the human. I think it's coming from having a complete vision of the whole. It's coming from having a complete vision of the ecosystem. So the environment in response of the vehicle, the driver state in profile, as well as the vehicle onboard sensors. So I think this is the whole ecosystem, and not just like picking some of the parts. This is the challenge for this part. And therefore, I think that the goal of this workshop was to see and to explore and discuss with all of you some of the aspects that can help with car accidents prediction and human behavior understanding. So here's the schedule of today. So I mark it here. You can see. So for some of you, it's Friday. From I think it's no, it's Saturday. I just put it. I don't know why did I put that. So it's the timings are not correct, but yeah. So I'm going to do the opening. So we have 2 keynote speakers. And we have also Professor Neng Chao Liu, who's invited, and he's going to give a talk. And we have also 2 student presentations. So I'm not going to spend much more time on this. And I would like to welcome Dr. David Serkin, who is the Executive Director at Stanford University Center for Design Research. And so he's going to speak about why are our cars acting this way. And I think it's going to be a really very exciting presentation. So I'm going to stop sharing, and the floor is yours, David.
Okay, thanks, Adriana. Hi, everybody. Let me set up my screen share here. How do things look? Is the right-hand side covered, or does it look okay?
I think it's okay.
Because I can hide the right-hand side, then I can't see you all very well. But maybe that's the best thing to do. Okay, how's it looking now? Any different or exactly the same?
No, it's perfect. Now we can see the stop sign. Yeah. So before it was covered, and now we can see the full screen. So that's perfect. Thank you.
Okay, and is the top clean too? Because I have the
Yep.
little zoom, stop share button. So the top looks
No,
okay?
no, that's perfect. We can see everything.
Okay, great. Well, that wasn't too painful. And let me check, what's a good time for me to finish? Because I probably have more than I'll have time to talk to, so I'll pick and choose as we get near the end of time. So when should I start looking?
They have half an hour, so around like 40, 45, that's fine. So you can.
Okay, that's fine. So hi everybody, I'm David. I am a pretty interactive person, so that makes it good that I study interaction design, right? But that means that I like conversation more than just me dialoguing the whole time. So I encourage you to interrupt me and ask me questions as we go. If I don't reach all my content, that's okay. The conversation will be more interesting than the content would have been. So please speak up. Happy to hear from you all. I won't be talking about accident prediction, but I will be talking about human behavior, and especially ways that we can study it. So at Stanford, our group's research is to design and understand interactions with automated systems, whether they are robots or smart handheld devices or mobile devices or self-driving cars of the future. So in today's talk, I'm going to show, I gotta move something out of the way here. So in today's talk, I'll show a few of our studies of self-driving cars, on the road, in simulators, and online. And I'll focus on the techniques that we use to design the interactions, and I'll include some insights along the way. So let's see. Oh gosh, my presentation here is not cooperating very well. Let me move my screen a little. See if this helps. No, I'm going to stop sharing and then reshare. Let me restart this. I see what's going on. Pardon the delay. I'm juggling the Zoom display and the PowerPoint display, trying to get them all to show up. Which I can only kind of do. It's interesting. It's not usually a problem, but we'll deal with it. Okay, I'll go back to sharing again. Okay, hopefully we're back in business. So in an interview in Popular Science magazine in 2016, Rafik Krikorian, who was Uber's engineering director at the time, said, if we can drive in Pittsburgh, we can drive anywhere. Now, 2 years earlier, Uber had just acquired a raft of roboticists from Carnegie Mellon University and set up their own self-driving program. Now, what he meant by that was that the roads in Pittsburgh, which is in Pennsylvania on the east coast of the United States, and it's a cold place. So what he meant was that the roads there, they provided challenging real-world setting to test autonomous cars. It had narrow roads and bad signs and really variable weather. So I don't know Pittsburgh all that well, but over time, this notion of diversity in driving contexts has become a real challenge to automation. As Adriano was saying, it's still quite a bit in the future, and I think this is still part of it. And it's not really because of signs or weather, but it's culturally and it's socially. So in particular, a car that drives well in Pittsburgh, it may have to adapt to the weather. Oh, let me get this running. So this is kind of what Pittsburgh looks like. So it may have to adapt to different weather conditions, but the road norms don't really change. The same car that could drive okay here might have a more difficult time adapting to, say, the roads in the northeast of England. Now, it's not that the roads are necessarily all that different, but the way that they're used sure is. And a car that drives well on this road might not fare that well on a street in Vietnam. This scene shows what I tend to call awareness-based driving. And it's in contrast to the kind of rules-based driving that we follow in much of the West. Is anybody like from a place where this is the typical driving culture that you experience every day? No, I don't know. Nobody's chiming in, and I can't see.
Sometimes in my hometown, in the village, the motor car and vehicle and bicycle and people are in the same cross road, just like this in the village.
Yeah, you know, notice that there's no traffic lights or lane lines, but the crowds of cars and the scooters and the push carts and the pedestrians, they manage just fine. Like, people are just improvising their way through the interaction. And let's see. So, whereas in the West, we have this notion of follow, as I was saying, rule-based, kind of follow the rules. And one of these sort of implicit rules is this idea that when people, you would expect that when people approach an intersection, that the pedestrians will look to make sure that they can see the driver see them before they feel comfortable stepping out into the road. Now, that's certainly not what happened in the last scene that we just saw. But if we go with that for the moment, in the future, when there's no driver, how will these people who look to the driver for what to do, how are they going to negotiate when it's their turn? And that question set us off onto a line of research. And to study the question, we wanted to be able to improvise interactions just like people were doing in Hanoi there. But that's beyond the ability of today's self-driving cars. Even if we could access a self-driving car for a study, which we don't have one. I mean, we have some that'll drive down a controlled road for a little bit, but not out in main flow of city streets. So basically, we needed a car that would have a human driver in it, but not look like it had a human driver in it. And our solution looked something like this. And I'll show you a video in a moment, but we've run a number of studies using this setup in the US and Mexico and Netherlands. And overall, we've observed that people really don't look at the driver all that much. They tend to look more at the car and its motion and its behavior. And as a result, we now suspect that the driving behavior and movements are more important than the driver and may be sufficient on their own to signal to other road users, cars and pedestrians, what the car's intention is and how they should respond to it. Here. So I'll run the, do I have more here? Is that it? Yeah. But when we were running these studies, we were a little surprised to find that some people became abusive towards our car. Maybe on the bullying side, maybe just on the curiosity side, but I'll have a video that'll show you our experiences. So this is just a hidden driver inside of a car seat costume. See, thumbs up. He just steps out towards the car, just to see what it'll do. They wait there at the traffic island for the car to go in circles and come back, just so they could walk in front of it. Now this lady goes and tries to open the car door and get in. Fellow stood there for 5 minutes taking photos. They just cursed at us. This car just stomped on the brake to see if we would crash into him from behind. Twice. What else can I say about that study? So that study was, I think we spent, I'm sure that automotive companies testing cars on the road are seeing that kind of behavior, but they're probably not reporting it. It doesn't really serve them very well to report it. It took us about 24 hours of driving on the road to capture those kinds of behaviors. I expect as the cars become more common that will kind of go away, but for now it's still, they're novel and it's still something to do, I guess. And the on-road prototype that we just saw was for studying interactions outside of the vehicle. Now, this one is for studying interactions inside of one. Now, in both cases, we're just hiding a human driver. Either we're hiding them from people on the outside of the car, or we're hiding them from people on the inside of the car. And so what we do is we fit a foam core board, which is this thing over here, between a researcher who's driving the car and a participant who's in the passenger seat over here. We tell them, don't look over the wall and imagine you're in a self-driving car. And we just Velcroed an aftermarket steering wheel and a little tablet onto the dashboard as sort of a super cheap infotainment system for them. And this is our study platform. And this is the way the system looks in action. Now, the driver is behind this partition up at the top right here in red. And an experimenter is in the back seat over here in red. So he's operating the interface that we're testing in the study, which is what the lady in the bottom corner is doing, raising her hands. That's the study. But having him in the back there also turns out to be a really convenient form of misdirection, so that they're paying attention to him instead of the real driver that's hidden on the other side of the wall. Now, yeah, it doesn't really matter too much, so we'll move on. So here's a video of a study using this setup, but it's focusing on the participant's experience. It's from a couple years ago now, but it shows how the prototype works.
How did the dive go?
Oh, it's pretty amazing.
Go, Otto.
Oh. I guess the computer is pretty awesome. There's a number of obstacles that I could have imagined being pretty troublesome for a computer car. It seemed to navigate through them all. A flock of people on the side of the road on this really small street, like construction and like traffic and all these different situations where it just basically did the right thing. Yeah, it was a much better driver than most humans today.
So how did the ride go in general terms?
I was impressed. It went very well.
Did you feel nervous at any point?
I did. There was a construction site that we went past. There was a construction vehicle and the guy was waving for me to move. I sat there like staring at the thing. I didn't wave to the guy or anything.
How responsible she feels for the way the car behaves.
So the car backed up and then the guy made more hand signals.
Did you trust the vehicle?
I don't know. I just don't fully trust a car to drive on its own. Even though I had no bad experiences with this car, it just seems strange to me still that a car can drive itself.
We will now turn on the autonomous control, and the car will now greet you. Car, please say hello. Did you notice the car say hello?
I did.
What was it like?
It was an engine roar.
Okay. Did it make you feel uncomfortable or hurt you?
No, I thought it was very friendly.
Was it what you had imagined?
It was what I imagined. It was smooth, cautious, but normal driving experience. Kind of what makes it cool. I think I was surprised how much I trusted it. Even from the beginning when it said hello, that one thing gave it enough personality for me to trust it. It made me feel like even though it wasn't a human, it wasn't of malicious intent.
It just was driving carefully, slowly. Actually, it reminded me of a driving school instructor.
Was this pattern of driving okay with you?
Oh, it was ideal. I could definitely own one of these. How do I buy one? Do you think in 10 years?
So let me just check. Is the audio and video playing okay for everybody? Can you hear everything and is it moving smoothly?
Yes.
Yes.
Okay, great. Just making sure, because I don't want to get halfway through the talk and then somebody says, wait, I can't hear anything. So there was a portion of that video that I want to play back for you quickly. So I want you to pay attention to what this gentleman says here.
I think I was surprised how much I trusted it. Even from the beginning when it said hello, that one thing gave it enough personality for me to trust it. It made me feel like even though it wasn't a human, it wasn't of malicious intent.
Really? All the car had to do was go vroom when he sat down. And that was enough for him to feel that he could trust the car because it said hello to him. That's kind of interesting. I don't know. To me, this is the kind of insight, and I think this is an insight. We even call it the hello effect. It's not, you can't discover how this one gesture affects experience by engineering in a lab. And typically, by the time companies test their features with users, they've already locked in the design. And so it's too late to adjust the core concept. And so we espouse that people prototype their ideas and the interactions early, now, when you're still sort of conceiving things. And we've evolved the system. So right now, we use a right-hand drive car, which puts the participant on the left-hand side, which is the usual seat for a driver here. And we mirror the real steering wheel, which is on the right, on a gaming wheel on the left. So it's got a much more active feel to it. And then we add a tablet for the interface in the center stack. And in this study, we're just testing how the participant situation awareness evolves over time using something on that app.
May I ask you a question, David?
Sure.
Yeah, so did participants know that there is a real person on the right driving?
Right, that's a good question. Some yes, some no. We tell everybody in the setup for the study that there is a human driver. So this is generally not a deception study. We're not trying to lie to them, but we are trying to conceal best that we can that there is a human there. So we tell them, but then we do everything that we can to misdirect their attention away from it. So we will drive the car up to where we pick them up in such a way that they are positioned so that they can't see the driver. We seat them in the car such that they can't see the driver. And by having somebody in the back seat, in this case, it's me, that causes the participant to be aware that somebody's back there, but not know what they're doing. So maybe they're driving the car, maybe they're doing something else, but it helps. It's kind of like a magician doing sleight of hand. They say, oh, look at this over here, while they pick your pocket over there. You know, it's misdirection. And so we practice misdirection in this, and it gets to be pretty convincing, even though we tell people that there is a human driver. I think our typical rate is 25 to 30% still think that the car is driving itself. And admittedly, this study is from a few years ago, so it would probably be more believable now. But, you know, for the things that we're studying, it also doesn't matter all that much because people are very good at suspending disbelief. You know, you go into a movie and you see a sad scene and you cry, even though you know you're in a movie, you know, you still throw yourself into it. So we kind of rely on that to a large extent for people to behave in a naturalistic way. Good question. Any others?
Well, I want to ask those participants. Most of them seems like the students in Stanford or the researchers. Maybe they have too many knowledge about the driverless.
Too many what? I'm sorry.
They have too much knowledge about the driverless driving, and this kind of knowledge about this field. Maybe this will influence the results of the experiment.
That's also a very good. That's a very good point. Also. The first study that I showed, the one that had the cars driving in the car seat costume and people sort of stepping out in front of it, I wasn't calling it out at the time, but we ran that study in 3 or 4 different locations around the world in order to check if there was an effect of people being too familiar, just like you're saying. And, you know, surprisingly, we saw very similar behaviors everywhere we went. People behaved pretty similarly. What we were really studying was people's willingness to step out and cross in front of the car when they couldn't see a driver, you know. But everybody was pretty comfortable with it most everywhere. In some places, like when we were in a small town in the Netherlands, the car drew a bit of attention because they're not used to seeing those kinds of cars around. So people would do whatever they were doing, but once they crossed the street or whatever, they would probably stop and watch it more and see, you know, check out if it was behaving correctly. But we didn't get like hordes of people following us in one place and not another or something like that.
Thank you.
Was there something in particular that you were concerned?
Yeah, I'm concerned about that. I don't know whether these participants, where you found them, from online or experienced drivers or students?
You mean whether they're just, I want to make sure I'm understanding. So could the participants around campus in California be too familiar with self-driving cars?
Exactly, yes.
Right, and that, I you know, we used to think that, but I kind of don't anymore that much. I think the idea of self-driving cars is pretty ubiquitous around the world. They're not all that commonly seen everywhere, more commonly seen here. So that's why I was saying they drew a little more attention in other places, but we didn't get the impression that they were really changing people's behavior. It's hard to say. But a lot of those videos that I showed earlier, those were people in Mexico or did we have any in Japan there? We've done studies in Japan and in other parts of the US, and we see pretty similar behaviors. So I think it is definitely something that researchers should be aware of and concerned about. You should probably address it if you do a study in one place, it probably belongs in your limitation section. We only ran this study, you know, in California, so we don't know that it's necessarily the case for other places.
Thank you.
That's kind of the way I would think of it still at this state. It's not something to ignore yet. But still, like I said, we do this misdirection, and we had the researcher in the back, the Confederate in the back. Having researchers in the car can still change people's behavior. Are we already at time? Oh my gosh, where did the time go? Sometimes we just want to interact with drivers when they're driving on their own. So this setup uses a text-to-speech and a webcam to let a researcher talk to drivers using the voice of the car. So I'll just let this run for a second.
How is the build quality?
Not that good. Not that good.
Can you describe what is not good enough?
Yeah, I mean, for example, you know, this part on the door is doing some noise, quang, 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 when I put my arm on, and this is definitely not acceptable on this. I mean, this range.
I mean, this is just real time in the field need finding, right? And one thing that we saw was like that door panel is a natural armrest, right? He's got his arm on it, and it seems worth knowing how it could bother some customers, and so it can be addressed before production. But the point is that, you know, controlled field or lab experiments are tools to test hypotheses about interaction, and they're really good for that. But uncontrolled explorations like this, where you just put something in a car and have people interact with it, they can be even more valuable in discovering needs or insights that could lead to the hypotheses that you later test. So different tools for different, research goals, I guess. I'm going to show one more thing, and then I'm going to try to wind us down. And also, like I said, I had more than I would have time to talk about. This is the experimenter's interface for that system that we just saw. It shows the live CAN data, the data coming from the car here in the middle. And down here is where an experimenter enters the expressions that they want the car to say. But an interesting thing happened when we were chatting with some participants. So listen for her pause. Let me go back.
Do you feel that car
Listen to her pause in answering the car's question.
Do you feel that car changes lanes smoothly
See,
while
the brakes
engaged?
came on. And
it felt.
see, then finally she answers the question, but it took her a long time to get around to it. And that tells us that the interruption came at a bad time. The driver was busy braking for traffic instead of focusing on the question. So it turns out that there are good and bad times to interrupt drivers. Now, this observation led to another study of what makes drivers interruptible or not, but it highlights that makers of, say, navigation systems haven't necessarily done a lot to address in their interfaces as yet. When you're a quarter mile away, it tells you you're turning a quarter mile away, or however many meters that might be. Might it not be better to wait until the driver is receptive to that message, delay or postpone it a few seconds, and then deliver the message? Seems to me. Since we're pushing being out of time, I'm going to move to a closing slide. So as takeaway for the studies, first, when you are interaction prototyping, first, you should only build what's needed to learn what you're trying to understand, right? The goal, at least at first, is to try to understand people, not the technical implementation. That could mean using Wizard of Oz or janky foam core walls or whatever it is. You can always increase fidelity, system fidelity later, once you know what problems you want to focus on. The second one is Reeves and Nass showed years ago repeatedly that people treat computers socially. And we see that same effect in our studies too, that interactive systems are inherently social and they should probably be designed to follow humans' social norms. I'd argue that these norms and rituals are central to human interaction, and interactive systems such as vehicle HMI should probably follow them. Sometimes a subtle or unexpected cue, like an engine roar, it can communicate deep meaning and it affects trust and usability. Okay, I already said that, so I'm going to move on later. So sometimes sending a message is important, and sometimes not sending a message also is communicating. And it's usually communicating something not that good. So it's good to pay attention to how people are interpreting messages and non-messages. And as I noted, well, this relates to a study I didn't have time to show, but as I noted in the start about driving in Pittsburgh versus Hanoi, context is important. The norms of where you are studying is important, whether it's in Mexico or the US or California near campus. Try to run studies in more than one setting in case the context mediates the effect of the thing that you're manipulating. Sometimes the context is more important than the thing that you're manipulating, and it overrides it, and it's good to know that. So we're a minute or two over my time, but try to finish quickly. By the way, this is my email address. I'm happy to talk with you all to discuss, needs and driver states and emotions and new research approaches. Send me a note. Happy to hear from you.
Hi. Very nice presentation. Thank you very much. So I will let the others, and I will ask you a question at the end that I may have. So are there any questions? No questions.
Quiet crowd.
Yeah. So I really, so of course, that's also the study that we are doing in general for everything. We know that like human robot interaction, human machine interaction in general. So the humans are unpredictable. Okay, so you don't know exactly how they will behave in different situation and context, as you said it also earlier. Mm-hmm. So sometimes, like in your study, did you start it from like a hypothesis that you were expecting to have this kind of behavior, or is it much more like kind of open kind of study? Of course, so you had some idea, but you don't, of course, you cannot know. I don't know how many participants did you had, but you don't know exactly what you can expect at the end. Okay, mm-hmm. So as you showed, like the man with the arm. So that's something that not everyone will like arm arrest. That's something mm-hmm. that bother him, but maybe you could not expect that necessarily from this person necessarily, or person in general, mm-hmm. or other kind of. So can you please elaborate a little bit more on that? So how do you start for your experiment?
Okay, great. So so of the studies that I showed, and there was one or two that I didn't show, there is a mix of studies that are kind of explorations of an idea, and some that were much more controlled studies.
Okay.
So we will run studies online, which is a controlled, I guess it's a quasi-experiment. But we run studies in labs and in simulators, which is very controlled. I didn't show any of the simulator studies now, but we almost always start, if we have an inkling of an idea, like a student is riding his bike and he says, hey, this is a four-way intersection. If I can't see the driver's faces, how am I going to know it's okay to go? So, we often start with an inkling like that comes from someone in the lab, and we will then develop one of these kooky explorations. They're usually cheap, fast, and they're often what we call breaching. I don't know if you know that expression. I don't know if everybody else does, so I'll describe it. There are certain norms in any context, whether you're in a restaurant. There's a norm for sitting in a restaurant. You tend not to stand up and do jumping jacks while singing in a restaurant. That's sort of breaching the norms of that context. And so we will often put together these quick little explorations, like we'll put that microphone and the camera in the car and then send it out on the road with some people. And we will just talk to them and see how it goes. Or we will make a foam core wall and put it up and see if that works or not. And so we just come up with kooky ideas and we try them. And anybody can come up with kooky ideas. They're just cheap. You can have a monitor, have somebody sit in front of it and show them a video of somebody driving and have them turn a steering wheel. You can make a homemade simulator in a day. So we use these quick, dirty explorations to flesh out that inkling and see if it is a real phenomenon. And sometimes in doing that, we come up with new platforms that it turns out other people can use, like a hidden car seat costume. And then from there, we move towards a more controlled study to try to explore that phenomenon. In the study of pedestrians, the first study was just to see if pedestrians would cross. But after we did that, we kept refining the protocol. We then decided, okay, let's try approaching the intersection in different ways, stopping at different distances. Let's use a sound. Let's make it so that the sound changes pitch. Let's make it so that the sound doesn't change pitch. And then we would run each of these as another controlled experiment.
Yeah,
So
thank you very much. So this was not necessary for me. I know a little bit of your work, but it was also for the students in general, because there are some of them here. But so the idea is they have the impression that they need all this kind of very well-designed kind of experiment, or go only on the technical part. And so that's someone outside also that can say some of the same aspects that for some of my students also, but in general, so we are discussing that.
Okay,
So thank you for this reinforcing.
I'll give you another piece of that. When you look at a paper, the paper is always written retrospectively. You've already had the inkling. You've already run whatever, rough prototype. You've run a study or two, you've analyzed your data, and you write out what you did. Now, if people really wrote out what they did, the way they did it, they would be very different papers. People would say, oh, we ran an experiment and there was no effect. So we ditched that experiment and we redesigned it and ran it this way. But people never tell you about the study they ran that had no effect. They only tell you about the study that did. And that's not really the way research progresses. It's much more stumbling forward, trying something, going back and starting over again, but that's not the kind of paper that people usually write. We've written a couple of papers that way, and they can work, but it's, again, a little outside of the norm.
There is one question from Les Song I can see, so.
Okay, I can't see, so you can maybe forward it to me.
Hi, hello, Tabius and David. Hi, David. I'm very interested in your research because I'm using conversation analysis to study human-computer interaction. So I was not sure if you know this approach, because
I do.
I see very much similarities in your research and our research, because you also mentioned about norms and patterns, like how pedestrians react to a driverless car. So if we do this research, we prefer a naturally occurring data, like instead of laboratory lab data, experiment data. So I was wondering how many data have you included in your data corpus to find out the patterns, the so-called patterns, like of the pedestrians react actions. And because this is interesting, I think this is already could already be a research, like how people react to drive these cars when they go across the path. But I think there should be enough data to see the moment by moment actions of the phenomenon. So I was wondering how much data have you included in your data corpus?
Okay, great. And I hate to give this answer, but I'm going to. It depends.
Yeah.
Now the question is, what does it depend on? So first thing is, it depends on, are we doing a qualitative analysis like a conversation analysis? Yeah. Or are we hypothesis testing? So do we need numerical data that we have to run G-power on to figure out how many participants we need in order to get an effect size of this large, so we will run studies like that if we're running them in a simulator or someplace that's very controlled study. And then we'll just do what it tells us. Maybe often there are 60 participants, sometimes it's 40 participants. If we're doing qualitative analysis, that's a different story. Because, you want to have enough data so that you can see that things aren't necessarily one-off. But even if they are one-off, that doesn't invalidate them because the phenomenon still happened. And so I think researchers can fall into, I don't want to say a trap, but I'll say it, of thinking that by doing exploratory research where you're trying to understand the way that things are designed and the way people interact with them, that you need to be doing scientific, quantitative hypothesis testing research. And you don't. They're different things. There is a place for both. And seeing something that's very interesting, you know, you can report on that. And it is a valid report. So that it's worth people knowing, even if it's one instance. But as you say, we try to capture enough data so that we will have more than one instance of everything happening. Especially for something like conversation analysis, it helps you see, oh, well, this happened a few times. If you know, we usually will try to run these studies over a course of several days to several weeks. Now, maybe that means that we're capturing, if it's just people outdoors interacting naturalistically, you know, like pedestrians, some number of days to, you know, a week or two has been about enough data for us. Sometimes when we're running, let's see, studies of humans interacting with robots, just sort of opportunistically walking up to our robots on the street, we can be set up on the street and maybe 50 people will come by and interact with our robot. That's great. We get 50 data points. If it's 15, it's okay. That starts to be enough. So it's
okay, yeah.
That's where the "it depends" comes in.
Yeah, okay.
And
Thank you very much.
Conversation analysis is great. We've used it in other studies before, even in the car.
Yeah,
Thank you very much. We are running a little bit late.
Sorry.
Thank you.
So thank you, David. This was a wonderful presentation. Very nice experiments and very nice insights. So thank you very much. If you have any other questions later, please contact David directly or let us know, and we can also communicate to the questions. So now I will invite Professor Nenghao Liu from Wuhan University of Technology. So he's going to speak about human factors and cooperative control in human-machine co-driving. Thank you. So the floor is yours.
Can you see my screen?
Yes.
Okay. Good afternoon, colleagues. I'm very pleased to report at the workshop. Thanks for inviting Professor Tapas. I am Ren Tao Lu from the ITSC Research Center, Wuhan University of Technology. I have done some work on traffic safety evaluation and human factors in ADAS and autonomous driving. We mainly carried out our research using driving simulators. Today, I will introduce our research, human factor, and cooperative control in human-machine co-driving. Before sharing the topic, please allow me to introduce the research group, Intelligent and Connected Traffic Safety and Control. At present, I'm the leader of the group. The team has 9 researchers, 18 PhD students, and 63 master students. We focus on the following research: driving behavior and accident prevention, intelligent perception and decision, intelligent highway and cooperative control, intelligent traffic and cooperative control. And we invite Professor Wu Taozhong as the group supervisor. Today, the topic shared unfolds from the three aspects. Firstly, I would like to talk about the research background. Autonomous driving vehicles are developing rapidly, according to the data of ITSC and China Autonomous Vehicle Marketing Survey. In the first quarter of 2022, the predicted market sharing of L2 autonomous driving vehicle in the new passenger car market will reach to 1/4. It is estimated that in 2024, the global L2 autonomous driving vehicle will be more than 33, and in 2025, the market rate will be more than 50%. This is a predicted market situation. The rapid development of the autonomous driving also brings safety problems. Vehicle accident occurs frequently. For passengers and the driver's perspective, they want to do more other tasks during autonomous driving cruise. They hope that the vehicle will be more intelligent and can free up their hands from entertainment or some other secondary tasks. And meanwhile, car companies hope that drivers can drive more carefully and respond immediately in case of any danger. Especially during autonomous driving, the existing human-machine switching mode is difficult to ensure that drivers can take over the vehicle in a short time. For example, this picture shows that in September 2021, an autonomous driving vehicle collides with a truck in China. The pilot system does send a takeover request. However, the driver didn't take any response. Yeah. Therefore, human-machine interaction and the switch control optimization during this situation deserves further research, I think. Actually, institutions and researchers has carried out research on human factors and corrective control in this area. For example, Professor Kolbe studied takeover performance evaluation system and method. Professor Winter studied human-computer co-driving beliefs and the human-machine computer interaction mechanism and other research so on. This is a Chinese version. In China, there are several research in human factors and cooperative control in this area from 2015. The main research institute includes National University of Defense Technology, Tsinghua University, Wuhan University of Technology, and Jilin University. This is a survey based on the National Nature Science Foundation of China, a very important foundation program in China. The research involves HMI mechanism, cooperative control, and personalized driving control, and so on. And some are a group. Based on the survey of the research, the main problems at present mainly includes 4 aspects. Firstly, during autonomous driving, pilot workload is insufficient, we think, and in takeover, workload is too high. And which variables are main factors for excessive takeover during driving workload? Secondly, driving performance is affected by environmental systems and human factors. How to evaluate this takeover safety and what kind of takeover is safer? This is a question. Third, drivers in different states will lead high workload and poor takeover performance. How to use this remaining sensors information to achieve a cooperative takeover. And last, how to optimize HMI to improve the performance. This is a conclusion of the literature review. Next, I would like to share two research cases by our group in this past 3 years. In order to improve the safety of human-machine driving takeover, we mainly focus on these 2 points. One is optimization and the tests of HMI in co-driving switch and cooperative control method for human-machine co-drive. This research is mainly supported by the National Nature Science Foundation of China. These are one of our group supervisor and one is taken by me. In order to test and verify our behaviors, this research relies on the test platform. At present, the research of human-machine co-driving is mainly based on simulated driving experiments, supplemented by real vehicle experiments. Based on the driving simulator, we developed the human-machine driving test environment based on a simulator in 2018 and integrated philosophical and psychological equipment. The platform includes intelligent and connected vehicle driving simulator, EEG, eye movement trackers, and so on. And the following shows the autonomous driving simulator and HMI. The simulator supports collecting the driving information and programmable HMI and level 3 autonomous driving functions such as lane keeping assistant and adaptive cruise control and so on. We also develop a program to allow the driver to conduct secondary tasks while in cruise. For example, in the bottom center, drivers have to find the different numbers. This is we call the third secondary tasks. Before discussing the case, let's first talk about what human-machine co-driving. A review paper published by our group in the Journal of Traffic and Transportation Engineering defines human-machine co-driving as follows. When the autonomous driving at level 2 or level 3 is especially at level 3 level, the vehicle has certain autonomous driving ability. But when facing dynamic driving tasks that the systems cannot handle, the drivers have to take over the vehicle effectively. The driver and the system cooperate to complete the transition or the switch. This is case 1. Cooperative takeover control in human-machine co-driving. At present, after the driver takes over the vehicle, the system completely releases the control from 1 to 0. For the drivers in secondary tasks, the cognitive load is pretty high. and the takeover performance may be poor. In view of this problem, can we propose a method to evaluate takeover risk based on the ability and provide a corporate takeover? We can analyze the problem from two perspectives. Firstly, system failure does not mean that the loss of all function of the autonomous vehicle. The control system and a small number of sensors can still be used. This is the one situation. Secondly, according to partly information, the gradual transition of control can help drivers adapt the unstable period and improve the takeover performance. Therefore, we proposed the following control framework for human-machine co-driving takeover. We propose that in some cases, the autonomous driving system can gradually release the control from 1 to 0 gradually. The first is to identify the takeover intention. We can recognize the takeover intention as lane keeping and lane changing. Considering the availability of some sensors, we think some sensors will still work. The local optimal target trajectory is planned. And the control of the system is to make the vehicle's track predicted local trajectory. And finally, according to the real-time driving task, and they can adjust the control weight of the system and the driver and take the weight results of the final output of the control. So this is a sharing control by takeover. In the local path planning, we consider that the takeover time is short and the available resources of the system are limited. Therefore, and we adopt the common S-curve trajectory model, which is used the sigmoid function to form a local trajectory curve. And for the driver model, we use the driver in the loop to simulate the driver's tasks. And meanwhile, the driver is in the loop operation data can be used as the evaluation index of this system. This is a total framework. And under the cooperative takeover control framework, the input of the steering, for example, we studied the lateral control. The input of the steering system is obtained by the weight sum of the two parts, the steering angle controlled by the driver and the input angle calculated by the controller or the system. In the transition stage, the system will evaluate the collision risk and instability risk of the vehicle and dynamically adjust the weight. And the bottom is the lambda s is adjusted based on the collision TTC, time to collision. In order to verify the performance of the cooperative takeover method, a driver in loop experiment was designed. As shown in the figure, the test vehicle follows the vehicle ahead in the right lane at the speed. In the process of the autonomous driving pilot, the driver is in the secondary task state. The task is to watch the video through a cell phone app. And after a random time, the vehicle in front suddenly changes lane to the left. At this time, a static obstacle is in front. the system sends a takeover request. When the takeover intention is lane keeping, the target trajectory is straight line, and the general lane change intention was selected as a lane change to the left. There are two options. A total of 28 subjects were recruited in this experiment. Each participant experienced 3 driving conditions. Condition 1 is only autonomous driving without any driving tasks and any takeover. Condition 2 is takeover with the cooperative control. Condition 3 is takeover without cooperative control method. And we use driving behavior index such as steering angle, adjust rate, or surrogated safety measurement such as minimum time to collision for the evaluation. The improvement of safety performance can be seen from the obstacle avoidance trajectory and the minimum time to collision after taking over. In the left figure, the cooperative control method used provides a small driving trajectory slope. This is a blue line, far from the obstacle, closer to the center of the lane. On the right figure, the minimum time to collision represents the safety margin after takeover. The comparing indicates that cooperative takeover was relatively high, the time to collision, higher than 0.2 or 0.2 seconds. In stability analysis and cooperative group, the peak value of steering angle is large and drivers are prone to excessive operation in case of emergency. While in cooperative group, it can effectively reduce the steering angle peak. It can also be seen from the yaw rate, yaw angle that the stability of taking over was better in cooperative takeover. Okay. And according to the subjective evaluation, driving workload of the takeover decreased significantly, and the technology acceptance model score of cooperative takeover was higher than that of exist takeover method. This is the one actually was research published in a journal in China. This is a top journal in China. Let's move to the second case, HMI, human machine interaction information optimization during the takeover. Before conducting relevant research, we need to pay attention to issues. The first issue is how to reduce takeover time and improve takeover safety by HMI optimization. The second issue is that whether the leading information can reduce takeover response time and improve the takeover performance. In view of these problems, we carry out simulated driving experiments to analyze the impact of different HMI on the takeover time and the performance. In this study, we designed 12 HMI scans and two different emergency driving scenarios. The control variable includes a standard mobile game as a secondary tasks. This is the same secondary task, and the takeover request leading time was set as 7 seconds. A total of 30 drivers data, including driving data, eye tracking, and workload, were connected. Next, I would like to introduce the independent variable, the HMI. The takeover voice, we have the different takeover voice includes beep and combination of beep and voice, ladies sound plus a beep. And the takeover events information includes display the events. This is a triangle display events information or hiding the event information. And the most important is a leading information. It includes a blank or a guidance information or a forbidden information. Guidance is a yellow array indicating that the left part or the right part is safe. And forbidden information means that some sensor detects on the red area means that there are some unknown obstacle with risk. We assume and believe that this situation, this information can be provided when some sensors are available in the future. That means that when the autonomous vehicle doesn't work, it doesn't mean that all the sensors doesn't work. Some will work and provide critical information. In the analysis of takeover reaction time, it found that both leading information and the voice type has a significant impact in the takeover time. However, the events information that didn't. We get an interesting fund. When providing forbidden information, the takeover time was shorter than that of the guidance group, which indicates that the effect of the forbidden information was more significant. In addition, the mode of beep voice was significantly better than that of beep. This is the difference. In the analysis of surrogated safety measurement by the time to collision, events information and voice type have low significant impact on the takeover safety performance. However, the leading information has a significant on the minimum time to collision. Both this information group was larger than that of the black group. That means the larger of the time to collision, the safer. Okay. At last, I want to give a summary of these cases. Firstly, the cooperative takeover control. We proposed a new framework, and the control weight will be gradually transferred to improve the takeover performance. System failure didn't mean that all functions were lost. A small number of sensors can still plan the path and identify and safer maneuver. According to the drivers in loop test, we found that local path planning, collision risk assessment, and dynamic weight adjustment can improve takeover safety, margin, and stability. In the HMI optimization, we tested the impact of lead information on takeover time and performance. We found that guidance and forbidden information reduces the takeover time. However, it put forward higher requirements for the system, for example, the sensors. Finally, I would like to report that we have recently made an improvement to the HMI for driving simulator, which can display more dynamic information through the programmable instrument. It can do more tests on ADAS and autonomous driving. Let's have a, yes, this is a programmable. The voice and the icons can be changed by our program. Here is we put this screen on the dashboard of the simulator. Okay, the above is my report. Thank you for your attention. Thanks for inviting.
So thank you for this very nice presentation. So any questions? I have a question after that, but I will let first to the others.
Hello. I have a question about driving simulation. You said that it's a dynamic display of the driving scenario. Maybe not too much is maybe more information is not good for the cognitive of drivers. What do you think?
Yes, I totally agree. In the very beginning, we designed our HMI more complex, I think. There are too much high workload, I think. But later we will see less and less information. This information has handled by the system, by our algorithm. We think is a much simple one. It's very, for example, we learned much from the ADAS system. For example, the Mobileye and some other L3 autonomous vehicle, the HMI. We think the simple icons will lead to a lower workload. Yes.
Thank you.
Any other questions? Okay, so I will ask mine then. So did you're talking about like kind of shared driving behavior because it's a takeover, okay? Did you also thought about like, or did you also test so the time, the time the individual, the driver didn't drive before, so was not attentive to the driving path? So if I'm not driving for 1 hour and after that the machine, the vehicle is going to tell me, please take over. It's not the same like I was not driving for 5 minutes and the vehicle is going to tell me take over.
This is a good question. Actually, one of my colleagues in our group, Dr. Zhang, Professor Zhang, he researched the driving performance and driving fatigue, and the performance affected by the driving time, especially the stealthy driving in autonomous in this situation. I think that the time will affect the driver's takeoff performance. Actually, when we face the L2 or L3 autonomous driving, some drivers would like to drive by themselves because when the autopilot cruise control is much more boring or sleepy. Actually, this is a characteristic we faced. I think, yes, this is a work deserves to research.
You? Other questions? No. Right. We're a little bit beyond the schedule. So now normally we would have had like interactive session and coffee break. So maybe it's not going to be like 10 minutes, but maybe we can have like, you can discuss between yourself or everyone, or ask any kind of questions if you may have, like for 5 minutes. And so we will come back at 9:40. Normally this is more like yeah, a coffee break.
Okay, thank you.
Hello, David. I don't know whether you are here, and I want to discuss about the things you said before about no message is also kind of interaction. Yes, that's very interesting because generally no information, no message means no information, no information means no interaction. But why no message can be one kind of important interaction because of the time between two actions, or
is our student, was it Li Song who is the conversation analyst who asked the question?
Yeah, he's a linguist.
Right.
Yes.
I'll bet he can answer this question better than I can. But generally, you know, I don't know, engineers certainly don't think the same way that you know, linguists or sociologists do. But I think it could be helpful to be able to think both ways, right? And in the world of sociology, being silent is not always a good thing. It doesn't only mean no information. For example, let's say I ask you a question and you don't answer.
Yeah, I feel nervous.
Yeah, I mean, what is it nervous, or is it maybe getting to be insulting? Or it makes the asker question, did you not hear my question? Did you hear my question and don't know the answer? Are you angry at me and are therefore purposely not answering my question? There's all of these layers that can be possible explanations for not receiving a message when you might have expected to get one. So there is an interesting, it's I guess it's in linguistics, but it's also in social science and relations that, you know, there's expected responses to questions, there's odd and unexpected responses, and then there are non-responses. And, you know, unexpected responses are kind of surprising. They can be good, they can be bad, but non-responses usually indicate that there's something wrong.
Yeah.
Right? Like that you weren't heard, or there is no answer, or the answerer doesn't want to answer. It's usually not a good thing. And so that's why I'm suggesting that it can be, and you see this in conversation analysis all the time. You know, is there a beat? How long is it before the answer comes? And how does somebody interpret that lack of response? So when you think about interactive systems, if the word in there, it's an interactive system, then it should be interacting. And if it's not interacting, then it's not sending a message, then it's going to be received in a social way.
Another channel, a social channel.
Yeah, I mean, interaction, as I was saying, Reeves and Nass, who did this computers are social actors paradigm many, many years ago, suggest that people respond to computers in social ways. And it's not because we don't know better. We know they're computers. We are just hardwired to treat things socially. And so, you know, people who design technologies can take advantage of this in good or bad ways. But designers should understand that people, you know, view interactive media socially, and therefore the way that interaction plays out is a social interaction. And therefore the rules of conversation analysis come into play.
Thanks. Maybe to think in the term of a social way can inspire more human-machine interaction inference or application. I think maybe it's the next generation.
Well, let me paste something into the chat here. Let me make sure I have the reference correct. Okay. You might find that an interesting book relative to this topic that we're talking about.
Thank you. Thanks a lot.
If you're not familiar with the book. If you are, then no problem. But I suspect you might not be, given the questions, because they do talk about these things in there.
We have it in the lab.
We have it in the lab?
You don't even have to buy it now.
I never know it.
Okay.
Okay.
So I think we're going to start again.
Okay.
So thank you, David.
Thanks a lot.
Sure.
So now we go to the next. I hope that Hawang Lu is here.
Okay, I'm here.
Yeah, okay. So he's going to give a presentation on simulation system for human in the loop driving. Okay, so the floor is yours.
So my name is Haoang Lu from Xi'an Jiaotong University. Today I'm going to introduce our work, which is a simulation system for human in the loop driving. I will introduce this paper from 5 aspects, namely background, simulated driving environment, simulated driving dataset, human in the loop evaluation with dataset, and conclusion. First of all, I will talk about the current research status of the automatic driving industry and the current popular driving datasets. The Society of Automotive Engineer defines 6 levels of unmanned vehicle, from level 0, which is fully manual, to level 5, which is fully automatic. At present, most autonomous vehicles are at level 2, and the few can reach level 3, which is still a long way from full automation. For a long time, autonomous vehicles still need human control. The perception of human behavior is added to the unmanned system, which is the trend and necessary condition for the development of automatic driving. The existing popular driving scene data set only involves the image data of the driving scene outside the vehicle and cannot be applied to the driving scene of human in the loop. In order to fill the lack of this kind of data set, this paper constructs a simulated driving environment, focuses on the modeling of driver behavior, and constructs a data set for evaluating human in the loop system. The second part is the simulated driving environment we built and how to add human behavior to the model. First, the spatial layout of the simulated driving environment is shown in the figure, which can achieve a high fidelity driving experience. The simulated driving system uses the road traffic data set in color simulator to display the simulated real traffic environment on the circular screen. The driver controls the simulated vehicle through Logitech G29 analog steering wheel and the supporting pedal. Because the driving force shifter is not used due to the limitation of the simulation platform, the configuration of the G29 analog steering wheel turns off nonlinearity, and the driver generates a supervision signal for the traffic scene and feeds back the control command to color simulator at the same time. Color simulator records the scene data and the driver's control signal for the vehicle. Importantly, the simulated driver environment introduces the modeling of driver behavior. The driver's gaze and attitude during driving are collected to make up for the differences of all previous data sets. As shown in the figure on the left, if there's only a simple scenario, it's obviously difficult to judge whether driverless car should go straight, turn left, or turn right at the same time. Therefore, we have added the modeling of human behavior to understand the decision from 3 aspects. First, the driver's short-term behavior is analyzed. The scene in front of the car and the location of the driver's interest have a significant impact on the driver's decision-making. In addition, the posture change of the driver's upper body can also reflect his next action. Then the long-term behavior of the driver is understood, and it's found that the next action depends not only on the local perceptual input, but also on the navigation target. So we also have the local map with paths, which can also predict the driver's control signal to the vehicle to a certain extent. Therefore, a comprehensive understanding of the 3 aspects will eventually lead to a right turn, as shown in the figure. To achieve the above modeling of human behavior, the eye tracking sensor is used to record the driver's fixation point, and the internal state of the driver is modeled. The Kinect sensor is used to record the driver's upper body pose, and the external action of the driver is modeled. Using color simulator, we can record the driver's control command. Thus, a complete human in the loop simulation driving system is completed. The third part, we will describe how to build the dataset and what the dataset is like. In the process of simulating driving data acquisition, vehicles perceive the simulated road traffic environment through multiple sensors. A key point in this simulation is to use multiple type of sensors. Kinect sensor uses Kinect version 2.0 to capture RGB images and depth images synchronously and in real time. The eye tracking sensor uses the ETG eye tracking from SMI in Germany. The eye tracking is used to capture the driver's gaze and the scene he sees during driving. An RGB sensor and the depth sensor customized by color simulator are used. The RGB sensor and the depth sensor are fixed in the front of the vehicle and move along with the vehicle movement to obtain the first-person view angle in the vehicle for real-time recording of environmental data. The configurations of the 5 sensors used are shown in the left table. We have 5 sensors. We select the sensor with the lowest frame rate as the benchmark. Therefore, when collecting data, the whole process, you can see the depth sensor has the lowest frame rate. The whole process is that we turn off the Kinect sensor first, and we first turn off the Kinect sensor because it has the lowest frame rate, and then the eye tracking and the color internal sensors. When the collection time of a clip ends, we first turn off the sensor with the highest frame rate, which is color simulation environment. And then we turn off the Kinect sensors and the eye tracking sensor because it has low frame rate. The right figure shows a variety of highly simulated traffic environments, which use a variety of virtual reality map environments and simulate various weather conditions. We have different map and different weather conditions. The high coverage of the scene to the real world, the higher the accuracy of the simulation test results. Considering the diversity of driving habits of different drivers, the data set is composed of driving data of 14 drivers. In order to collect the responses of different drivers in different driving scenarios, 7 map environments are used in our dataset collection process, covering urban, suburban, rural, and highway scenes with different weather conditions, as I mentioned before. As shown in the table on the left, in addition, the simulated vehicle used in the data acquisition process are all small vehicles, cars, mostly cars. And their kinematic parameters are shown in the right table, which provides some reference information for users who use our dataset. Next, we need to process the collected data. Because the acquisition cycle of each sensor or the startup time is different. So we must first synchronize or capture data. So the principle of time registration method is to take the sensor with the lowest frame rate as the core sensor. And we take its acquisition time as the benchmark to obtain the synchronous data of other sensors. For each frame of the core sensor, we look for the frame with the smallest time difference among other sensors for alignment to achieve the goal of synchronization of all sensors. The data captured by the eye tracking sensor also has the interference of external factors besides the driving scenes in the circular screen. Because the eye tracking sensor not only capture the scene, the screen, but also the other environment. So we need to remove the interference of external factors from the image and extract the useful data by matching the eye tracking image and the road image we have. First, feature points are extracted from the scene image and the image collected by the eye tracking devices. And then we need to match the extracted feature points. These matching points are used for homography transform of road image and the eye tracking image to achieve spatial alignment. Finally, we have the aligned image. We draw the fixation point into the scene image collected by the color simulator. so that the fixation point is added to the scene image. So we have one one image with fixation points. The driver's upper limb movements plays a certain role in the prediction of vehicle control. So we need to process the images collected by the Kinect sensor, estimating the driver's pose, and we only retain the driver's upper body pose because the others have too much noise. The process of processing the pose image is shown in the figure. The open pose algorithm, we use open pose algorithm to estimate the driver's upper body pose. Map-based autonomous car navigation largely depend on collected high definition map, but the high definition map are hard to produce and maintain, and are also difficult to process. Study shows that the model trained with two-dimensional coarse-grained map usually yield favorable effect. So we decided to take coarse-grained map with paths as the input data. After the above operations, we have obtained a simulated driving data set with 24 driving scenarios and more than 350,000 single class data. And you can see the table for detailed statistic of the dataset scale. The dataset file structure is shown in the figure, and the data collected at the same time are stored in the same folder after processing. Among them, action sequence.txt contains the original action sequence and the control value of the original steering, braking, throttle, reverse actions. Using the original control value, the dataset user can process the dataset accordingly for different tasks. In the first part, I will explain the enlightening ideas about how to use our dataset. Our dataset can be used to classify and predict the vehicle control. And the model trained with our dataset can be directly tested on the Carla simulator. The dataset provides different vehicle control parameters collected by Color Simulator. Users can label the control at a certain time according to their own classification standard. The table on the right shows an example of how the control signal can be classified. Next is the evaluation system of human in the loop. In the past, dataset only contains driving scene data. Decisions are mainly made by machines. We need to study whether adding human monitoring and internal state to the dataset can improve the effect of the control. The dataset we constructed is used to realize the interaction between human drivers and machines, so that both machines and people can make decisions. The basic idea of the evaluation system is shown in the figure, which when the switch is on, the machine mainly make decisions and the control effect of the model can be tested. When the switch is off, both machine and human can make decisions. We can then test whether the control can enhance through human-machine interaction. When trained with driver's behavior, since the driver's action is a continuous sequence, whose next movement is affected by the action of the previous movement, we should use a continuous sequence to understand the driver's behavior. Here's an example of how to build a model for training with driver's behavior data. Here we show an example. For the addition of drivers related behavior data, it can be processed separately to get one hot type command, such as left turn, straight ahead, right turn, and there will be a default command when there is no command. The driver's command is regarded as a switch to select the corresponding submodule, and all modules share the perceptual flow to generate the predicted action. When the sample distribution is unbalanced, the accuracy cannot reasonably reflect the predictive ability of the model. We often use confusion matrix to calculate precision, recall, and precision and recall. And we use macro F1, and weighted F1 as evaluation indicators. Suppose that the table shows the 3 classification results of steering control. For example, using macro F1 as the evaluation indicator, calculate the F1 value before and after adding driver behavior according to formulas here, formulas 1 and 2, and calculate the improvement rate of the model effect according to formula 3. From this, we can better evaluate the effect changes of the model there before and after joining the human behavior data. Then we come to our conclusion. By combining driver's ability with machine intelligence, we are trying to augment the system with the combination of both roles during driving. The human in the loop hybrid augmented system is expected to monitor and model driver's behavior. In this paper, we supply an effective way to monitor the driver and construct a simulated system for the human in the loop autonomous driving, which realize the modeling of driver behavior. Based on it, we provide a data acquisition scheme for both driver behavior and scene content, and subsequently construct the corresponding data set. The simulated system and the data set can help the community to develop such human-in-the-loop system. For the constructed data set, we provide a method for evaluating human-in-the-loop system. So that's all for my presentation. Thank you all for watching.
So thank you for this very nice presentation also. Again, I have a question, but later. So any questions? No one. I would like to know, how do you take into consideration so the uncertainty of data, so that you acquired also with your sensors, and so the reliability of your sensors usually when you are dealing in these systems?
So sorry, I didn't quite understand your question.
How do you deal with the reliability of your sensors?
Reliability of sensor. We just use sensor we can purchase. So there are definitely going to be noise in the sensors, but it can be ignored because it has little effect on the general position of our data set.
Okay, thank you. Other questions?
I have another question. Is this system built on rules?
What?
I mean, the Caroline also have a RUS API, robot operating system. Is this data system built based on RUS?
No, we use color simulator.
Okay, thank you.
So is there any other questions?
I can't see any hand raised. Okay, so thank you very much. So we go to the next keynote speaker. So I would really like to invite Jean-Baptiste Oé, to come and give his talk on automation for humans from error correction to support. Hi, Jean-Baptiste, can you share your screen?
Hi everyone. Okay, I needed that the previous sharing was stopped. So
yeah, indeed.
So important question. Can you see my screen?
Yes.
Okay, great. Everything is working. That's perfect.
Perfect. So the floor is yours.
Okay, thank you. Hi everyone. I'm very happy to be here. My name is Jean-Baptiste Oué, and I'm leading the driving behavioral department at the lab in France. So next slide. Okay, my mouse here. Thank you very much, Adriana, for this very nice topic of workshop. So today, I would like to share with you some observations that were made about the interaction of automated vehicles with human driver within the traffic. The interest of this observation is that it reveals somehow how human drivers are driving, but also to compare that with the automation behavior. The interest here, because we are funding a new framework for AI, is to give some insights, some ideas about how we can take the best between human and automation. So I will use this observation through a journey to question the perspective where automation is aimed at monitoring and correcting human errors, and to propose another complementary direction where AI can be used to empower drivers. So if you are okay, but I guess you are, let's do this. I think you have already seen this, this kind of figure. It's about the evolution through time of the road fatalities. These are the European numbers. I think it's quite similar in different parts of the world. This figure reveals something, that there were a trend starting well before 2000, showing a very good progresses of these fatalities. And these progresses, when we look quite carefully, we can see it comes from several kind of measures. First kind of measure is about passive safety. Using safety belt and airbag is very efficient to reduce fatalities in case of crash. Decreasing the legal speed or the legal alcohol level is also quite efficient to avoid the crash or for the speed, the impact of the crash. And then automation was introduced, also automation intervening at the last moment before the crash. ABS some time ago, and emergency braking that is more and more present in the vehicle today. But then the figures show that there is an inflection point here. It seems that the progresses are plateauing. So you can see the difference between the blue line, that was the European target, hoping to maintain this progress, and the real data. The question, of course, is, will this plateau continue like it seems it will be? The last years are not very significant, but we can imagine that there is a hard baseline. And I think you all have heard this number of 80% of accidents that may be provoked by human errors. So maybe the human errors are the remaining problems that cannot solve by this kind of measures. So if there are some human errors, we can examine that. What are the human weaknesses that provoke these errors? I've listed the most classical of them. Lack of skill for novice drivers. You know, it takes some time to automatize the efficient driving skills. Humans are not always do not always present some moderation, drinking, seeking the sensation of speed, sometimes falling into road rage. problem with health, sudden unconsciousness, for instance. It happens quite rarely, but it's often dramatic. Then there is an inconstant vigilant arousal level. We are getting tired when we are driving. Distraction, people sometimes dedicate themselves voluntarily to non-driving activities, and improper driving posture, especially with L2 systems, automation at level 2 of SAE levels, with the hands-on, hands-off issue. You can recognize that the four last ones are the classical driving monitoring perimeter. There are more and more systems targeting these elements. Okay, so the idea here is that we have found some weaknesses of humans, so we can try to use technology to correct them. We can monitor, we can warn. If the driver is not reacting, we can assist him by acting instead of him. Well, but the journey is not over, because there are limits of these countermeasures. When we introduce technology in human activity, it never works totally as expected. There are some what Brainbridge told ironies of automation. I'm sure you are quite familiar with some of them. Some people are voluntarily tricking the systems, for instance, using a bottle to avoid the hands detection system to alert them or disconnect an automotive driving system, for instance. There is also a process that is called risk homeostasis. The first model was presented by Wild. The idea is, if the driver feels safer thanks to a technological system, he will not just keep this extra safety level. He's likely to use it, for instance, to do more non-driving activities. So the idea is that the driver is maintaining a constant level of safety. So improving the level of safety, finally, has not a continuous effect. Another element is behavioral adaptation. So a good example is, if you increase the braking power of the car, you will observe that the driver will shorten their safety margins. In other words, the safety margin that are defined by drivers are defined according to the time they need to react to a specific event. So a better technology will lead to smaller safety margins. And the last and more subtle process is called complacency, especially when the driver is supposed to monitor an automation of driving, because he's responsible to take over if something gets wrong, is losing the pragmatic expectation that a normal driver has. He doesn't have to steer or to brake anymore. So he's just looking at the automation, and a bit like in a movie, when something is going wrong, he doesn't have the driving reflex that are ready anymore. And he could just contemplate the automation driving as the automation was doing, assuming that he will manage everything. Okay, so if we have some limits of this partial automation, another response could say, okay, so there are still human limitations, so let's replace human and having full automation. That would be the logical progression of that approach. Well, there are some issues about that. You know this. We know pretty well now that automated driving will take some time to arrive, or maybe will not totally fully cover all driving conditions. And there may be a second, more philosophical issue about this, about replacing human by technology. We can argue that any technology could be socially, economically, ecologically assessed before being introduced into a society. Okay, so the conclusion here would be, maybe that's interesting to question what is the interaction that we are targeting between human and automation. So this is about this question that looking at interaction between automated vehicles and human driver becomes interesting. So we can do that thanks to the SAM French project that was aimed at testing new mobility services thanks to automated driving. There are still, because the project is not finished, 13 experimentations on open roads, some of them in private sites, most of them with safety drivers. The data gathered by this experimentation is provided to 12 evaluation domains, including studying acceptability and user behavior, where the lab is participating. Okay, so the study is about looking at what are the perturbations happening between this automated vehicle and the traffic surrounding. Perturbation because the OEM are working pretty well. There are no accidents, no big incidents, so that's good for them, but there are very extra safety measures in such experimentation, of course. So what we can observe are perturbation. At this point of the project, the results that I will present you are based on data collected from safety drivers. Safety drivers are always attentive, looking all around all the time. So they are privileged observers of what's going on. But now we are pursuing some other studies to collect data from the perspective of other road users on the interaction with automated vehicles. The approach that was chosen was to collect scenarios about uncivil behaviors. When we talk about incivilities, safety drivers, as any driver in the real life, has a lot of things to say. Okay, other people are not behaving correctly. We are pretty good at noticing and qualifying what other people are doing wrong. And from this data collection, it's pretty easy to have people talk or to generalize about all the perturbation in the traffic, even if there is not this incivility content. This panorama of perturbation show what are the type of hazards that automated vehicle has to deal with. Okay, so from the 13 experimentation, I will show you some results from 3 of them. These data were confronted in order to generalize the perturbation and incivilities scenario. The studies were done by the lab, but also VDECOM. There are 3 experimentations, 2 with shuttles, and you can see on the left in the Rennes campus. Rennes is a French city, that there are some shuttles in very narrow streets. So obviously that's tricky. So the shuttles were in such urban conditions, but also on roads dedicated to pedestrians and cyclists. And that's interesting to compare what happens in 2 different contexts. And the third experimentation was on highways, with a personal car equipped with the equivalent of a L3 automated driving system. Okay, so let's go. Here are some examples of incivilities or perturbation that were collected from the safety drivers. It was quite surprising to see that one of the main issues, at least for shuttle, was about improper parking. Why? It's because especially the shuttle has very strict and narrow path, programmed paths where they are supposed to drive. And whenever there is an obstacle, the automation is perturbed and it stops. And then the safety driver has to hand over and to do something manually. So when there is an illegal parking, let's imagine we are in a Rennes campus, someone stopped his car 10 minutes near the administrative building just to drop a paper. as humans, sometimes we do that. Well, for the automated vehicle, that's an obstacle that it's not programmed to overpass. There is an obstacle, so the automated vehicle stops. And then the safety driver considers that the driver here has blocked the shuttle, even if the driver was maybe not aware of the consequences of parking here. There are other examples where the parking is not illegal, but just approximative. The driver was quite in a hurry, the room was maybe not very comfortable. And if the car is a bit on the lane, sometimes it was an obstacle for automated vehicle. And last variation of that example is not an incivility anymore at all. It's very hard to qualify it like that. There is a big vehicle, let's say a truck. Even if the driver was very careful to park as well as possible, well, it's too large, so it arrived a bit on the lane and it blocked the automated vehicle. Another interesting example, it was from another experimentation by Renault, was in an urban area, and the automated vehicle was aimed at mobility services picking up passengers on plain road because there was no room available on the side of the road. And even if some physical barriers has been put especially to avoid that, some vehicles were going the wrong way to not to be blocked by the stopped automated vehicle. And obviously that's a risky maneuver. Another example in highways, it's a very common example of short cut-ins, a vehicle that arrives with a short safety margin in front of us. The interesting point is we can imagine that all automated vehicles will not detect or interpret blinkers. It is not a so obvious function to be developed. So we can also imagine that a truck driver, you know, there is a kind of inertia to overpass another truck. So because he has put the blinker, there are some room available around. The driver may assume that a car will let him some space to do its maneuver, and being himself or herself surprised that the vehicle is still on the lane. So, you know, the incivility, it's very subjective issues, and they can have two very different perspectives on one situation. And the last example, it's a quite anecdotal but striking example of the social manifestation. In Rennes, there was one cyclist, one specific guy that regularly arrived and was punching at the vehicle, showing some protestation. And this person stopped after being explained that he could have a fine for that. Okay, so there are illustrative examples, and the question is, what can we do with that? Because there's a real diversity of situations, different kind of roads, and at this point, it's only collected from safety driver perspective. So we need to find transversal factors to sort that. So the choice that was done was to sort all the collected scenario according to the assumed motivation of the other road users. So, okay, let's talk about motivation while driving. And Sumala provide a very good framework for that. Sumala said that driving has several motivations. He specified 4 of them. The first of them is when driving, drivers are maintaining comfortable safety margins to avoid feeling at risk. A second one is to maintaining comfort. So you can think about body comfort according to acceleration, but also temperature, visual comfort, attentional comfort, etc. A third one is about complying with legal rules. So you don't have to worry to be fined, but it's also about social norms. Not respecting social norms, especially social norms we have been educated with, could worry us to have a bad judgment from other, but it's also about having a bad self-judgment of ourselves, because these are norms we have internalized. The last one is really important too, is about maintaining the progress of a trip as expected. When you are in a hurry, any obstacle is very stressful because you are already anticipating the consequences of being in a hurry. Even if you are not in a hurry, you are expecting a given path, a given pace of your trip. When something unexpected happens, it's quite frustrating because the plan is the quality, the projected result of the traveling plan is impacted. If you have some discomfort, if something happens in any of these 4 factors, you will feel some discomfort, Sumala says. And the normal driving comfort is when everything is going fine on these 4 dimensions. Sorry. So, for instance, when you have some pressure about time travel, the driver can be incited to have shorten safety margin. It's not comfortable, but it's a way of releasing the discomfort of the time pressure. And maybe it will also not respect some legal rules or social norms, passing everyone, because having some discomfort here is the way of releasing this discomfort. So there is a negotiation between these different factors. There are also some extra driving motivations. Sometimes you can have some curiosity, animosity, courtesy with the people that are all around you in the road scene. You can communicate with your relationship, passenger in the car, talking with people on the phone or with other devices, even texting. Of course, it's not good for safety. We all know that. Or any other personal matters, preoccupation, object, eating, whatever that people are bringing with themselves in their car. So we have found 3 interesting motivations to sort the observed incivilities. The hurrying motives, people rushing, it's an obvious one. The fact that sometimes a human driver has a loose respect of legal rules and social norms, and this question of social focus, social interest. So let's go. Let's use these 3 motivations. And it has been observed that indeed, this motivation can be found in different way in the different road types. If we look at highways first, the automated vehicle of the experimentation was inserting quite normally in the traffic. So what was observed was usual driving behavior, some hurrying driver targeting or overpassing with a very fast speed. And when looking at the automated vehicle insertion in the traffic, what was observed, it can be qualified as a very cautious driver. When we are looking at the loose respect of rules or norms, there are the normal approximative driving, right overpassing, shortcutting, even if people are not hurrying. It's not about being the fastest, but it's just not to make effort. And here, the automated vehicle in our currently going on studies by other road users sometimes are qualified as not really human-like. There are some surprising behavior that human drivers do not really understand while they are going to the right lane to overpass a couple of seconds afterward. About social interest, there were a few examples of curiosity from other road users staying here to observe a strange car with stickers and sensors, and some fast driver suddenly aborted their overpassing. We assume that they were thinking it was maybe a police car, a speed trap, and they were afraid to be fined because with excessive speed. When looking at the urban context, especially for shuttle, that's a tricky context because the shuttles often are slower. So they are kind of blocking the traffic. The vehicle cyclists frequently refuse priority or overpass and don't want to be blocked because it's too slow or it's stopped because to pick passengers. So quite often we have observed some dangerous behavior of people that don't want to be blocked by the vehicle. There is a very important diversity of vehicle, of behavior in urban conditions. People are not only displacing, they are not only in a trip, they are living there, they are talking with people, they are doing all kinds of stuff. It's a place of life. So the shuttle has to confront with a huge diversity of behavior. And I presented you the parking issue. There was a lot of curiosity of pedestrians testing the vehicle. Some vehicle that wanted to pass, that were arriving until they touch the shuttle here or the automated vehicle. So it's not only wanting to pass, it's also showing in a social interaction that they are not happy to be blocked. Finally, on pedestrian and cyclist path, the shuttle is faster than pedestrian, but often slower than cyclists. So there is a mix that's not so easy. There were some tension observed about sharing space, especially when the lane dedicated to automated vehicle has taken some space from the cycling lane. And some cyclists were protesting, obviously, according to that. Some pedestrian, especially it's within the woods during the weekend, so people are hanging around, there are plenty of disponibility on time to be curious about the shuttle, taking some picture, testing what happens if I stay in front of the shuttle, will it slow? And it's not very fast at the beginning, so there is no huge stake of safety because it's not going very fast. And here, some pedestrians sometimes are not making so much effort to leave the way. Is it a norm that pedestrians shall leave space to an automated vehicle in an experimentation? The automated vehicle was not here some months ago. So, okay, what is the need for the pedestrian to do that? It's not so obvious. Okay, so what is interesting here, firstly, is we can start sorting the scenario to show some factors, but every time that we talk about the behavior of the human driver or human other road users, we can see that the automated vehicle, its behavior also has an impact on the traffic. So now we can try to move forward to look at what are the impact, what are the responsibilities both of automated vehicle, of the automation, and of human drivers. So we can generalize the motivation we have picked up to stick with both human behavior and AI behavior. For human behavior, the hurrying motivation can be qualified as inadequate driving behavior. They want to speed up, so they show aggressive cutting, not letting priority, for instance. The impact is that other road user, including the automation driving, has to brake or to avoid this vehicle. It can be delayed or blocked. When we are looking at the automation behavior, the inadequacy is quite different. It's more about being defensive. Of course, when it's programmed, it's designed for safety, of course, and this is the way it has to be. But to be really safe, automated driving has to respect very cautious rules. So at the end, driving automation can be sometimes slow, can hesitate to engage, for instance, in a roundabout. That's pretty tricky, a roundabout. You have to engage with a lot of cars. And at the second you engage, you don't really have the gap to insert. So you have to rely on the other road users to adapt themselves so you can indeed integrate safely the flow of the vehicle. They may stop for obstacles that a human driver could easily adapt to. So finally, the impact on the traffic is to delay other road users and at the end to incite to overpass or other risky behavior. The loose respect of rules, norms, finally, it's a lack of coordination with other road users. I presented the improper parking, the positioning in lane of human driver may be approximate to. For AI behavior, there are some tricky driving processes about, for instance, implicit communication. You know, this truck driver that is assuming because there is plenty of room around that the car will help him doing his or her maneuver. These tricky processes at the beginning of automated vehicle, it's not the priority. The priority is safety. And this function may not be developed or may take some time to be developed. So if the automated vehicle do not present this behavior, maybe there is not a huge safety stake because automated vehicles still respect rules normally, but they could have negative judgment on something about acceptability. The last one, social interest. Finally, we can say that human drivers are manifesting some behavior about non-driving goals. They are not driving, they are spending some time looking what is going on around. Another non-driving goals for automation is the mobility services. That would be the same for a taxi or a bus. But when the automated driving stop on the plain road or to pick up passengers, that has a big impact on the traffic around, and it could incite to overpass. So continuing with this comparison, we can see that both human drivers and automated driving has some domain where it's not so good to cope with that. So we can now try to push in that direction to look what are the strengths and weaknesses first of human. Let's start with human. We have seen that the way human manage risk can be described as an homeostasis. According to the context, the different driving or non-driving motivation, humans are balancing, negotiating between the safety margin and other factors. The real strength of human driver is that they are flexible and they can learn. They learn all along their life to improve their driving skills with experience, hopefully, for most of them. The negative part is if they can learn, they are not very constant. One day they can be in a good mood, very calm and zen, and another day they can be they have spent hours in traffic jam and they are tired and with problem at home and everything, so they are not constant. If they are flexible, they are so much flexible that sometimes they can even negotiate safety rules. And negotiating too much safety rules, we know that at some points it's not good. They can project themselves to non-driving activities, but they're also able to anticipate some driving risk with very low signals, which is an incredible capabilities. About social interaction, the best and the worst, they can be very courteous to others according to people and the time of the day and whatever, and sometimes they express aggressivity. In comparison, the behavior of automation is really different. Why? Because an automation is not doing anything more than applying the rules that were programmed by the designers. So the AI will respect the rules, the program rules. And this is good because when it's good rules, it's nice to respect them. But in specific situation, when I don't know that there is a hard white line and there is an obstacle on the lane, there's no way of staying the whole day blocked here. A human driver knows, and even police officers know that it's okay to pass cautiously the solid white line to go through. But that's very complicated for automation, for legal, ethical, and engineering and safety reasons. But applying these rules has another benefit of being constant. Perception and behavior will be always the same in the same context, of course, in nominal situation. So it's highly predictable. On the other way, there is no adaptation possible. Right now, AI is not a program to learn. And if it was the case, we don't know what it could learn. So it sticks with the rule again. It will show the neutral courtesy that will be programmed, but will never show a specific empathy with a given driver or other road users in a specific context. The maneuver will be for sure well designed and well calibrated, but some of the functions for more tricky or implicit processes of interaction with the traffic may not be implemented at the beginning of the day. So, okay, now the idea is we have seen some strengths and weaknesses. The idea would be to take the best part of each. So we can, and this is the existing human-like approach, we use the example of good drivers' behaviors as an inspiration to specify, develop the driving functions that are implemented in automation. That's a very good inspiration. And on the other way, of course, automation can warn and correct human driving, but if the drivers are willing to do so, it could also provide with a reference of rules behaviors to develop the human own skills. A good driver will not need that for sure, but novice or anxious driver may be happy if it's well done to use this pedagogical and reference of good behavior to improve themselves. Okay, so how can we rephrase that? The proposal today is to redefine the safety paradigm, using the best of AI to get the best of drivers. Let's go back to this figure we were looking at the beginning of the presentation. Maybe we can say that the progresses that has been achieved was achieved by some structural measures that work in all situations, have a strong probability to improve all the driving situation. And finally, this hard baseline, if it indeed continues through years, maybe it's a diversity of specific situations, of specific errors and risks that require an adaptation to this local context. So something that cannot be addressed with a general rule. What can we do for that? We can get some inspiration in what is called the safety paradigm. So it has been applied to organization, factory with workers, or healthcare facilities in the medical domain. Not so much to driving yet, but we can get some inspiration from that. The idea is to move from the classical safety paradigm, which is called safety 1, where risk is defined according to as an error to the prescribed procedure. So the assumption here is that the procedure has the truth of safety, will solve all problems, and the procedure can be the algorithm of automation, it can be the procedure of activating, deactivating, and ADAS. So the good way from this perspective is to train the people to fit with the procedure, to correctly respect the procedure. There are some issues here. First, drivers are trained only at the very beginning of their driving career. And we also know that under stress, even someone who is trained with the stress may come back to his natural way of doing things or may not respect the procedure. Plus, the procedure may not be adapted to all the specific situations. So the idea is to move toward what was called safety 2, because 2 is better than 1, and then to focus toward a decentralization movement. We don't know by advance what will be the risk in a given situation. So we want to improve the capacity of organization to help people being able to adapt to this specific situation. So the way it was formulated in this safety 2 paradigm was to tune the matching of the system functions to match the cognitive processes of driver with the automation function to optimize safety. How could that be? And that will be the end of my presentation. Finally, it's to design an efficient human automation interaction, as it has already been said in previous presentation. So how can we do that? Something that seems important is to see how the system made by the driver, the vehicle, automation, and the traffic, how is that system behaving in the wild, in real situation? That's harder to do for sure than the simulator studies, but that's important to see the real situation of driving under diversity. Then we can see how do people perceive the driving situation, and this perception will make them perceiving safety and interpreting and behaving. How do they use ADAS? How do they not only making errors, but correctly managing risk, because it's a good inspiration. Then we can train the monitoring of the current risks of the situation. There are some distracted and hurrying drivers all around, we know that, but also to monitor how is the driver dealing with that, what is his or her attentional behavior and intent as far as we can predict it. If the driver is correctly observing and reacting, we don't need to bother him with some HMI that could be counterproductive by distracting him or her. And by looking at the adequacy of both, this is a good way to know when it's the good moment to help the driver. According also to the last factors, it's receptivity. If he's in the hurry of managing some driving events, it's not a good moment. So finally, we could hope to improve the design on how automation could guide the driver to adapt better and to learn through time to adapt better and better while driving. Through first, the motivation. All drivers won't be happy to accept some advice. What is this machine that want to learn me how to drive? And some people will be motivated only if there is, I don't know, financial incentive with insurance policy, for instance. Some may be happy to see that they are progressing, or just be happy to know they are improving, or they are well respecting good driving rules. There are diversity of profiles of drivers. It's about the content too. What is the content that is significant and useful to provide the driver? Of course, it's easy to say that people are overspeeding, but maybe overspeed, everyone is overspeeding here. Maybe there is no risk here to overspeed. So what is the adequate content? Risky vehicle, risky places. There are some infrastructure as maybe quite tricky to interpret. And of course, if the driver has already seen that, there is no interest in repeating something he or she already knows. Then it's about HMI and timing. What is the proper HMI to provide that? On timing, it's not the same cognitive processes. It's not the same needs for the driving to say to the drivers, okay, in some kilometer, they may have something, and maybe it's not interesting. In some kilometer, the risk won't be here anymore. It's something else to anticipate, I don't know, 10 or 15 seconds beforehand, preparing ourselves to react to something. When it happens, it's about reacting, and then we are driving, and the HMI could be about suggesting. We have no time anymore to read a message on the cluster. And when it's urgency reaction, it's just about urgency and reacting. So HMI and timing need to be respected. And then a last point, and I will be done, is maybe we can try to find a way, if the driver is okay, maybe by asking him what he's interested in, to provide maybe after the drive some feedback. So the driver can not only react in real time while driving, but from time to time, not all the time, or when we arrive, we have something else to do, but from time to time to think about his or her own driving, and maybe with adequate feedback and some good advices, take the opportunity to consolidate the driving is having every day and learning from in time. An example, a phrasing of that, maybe it's not only warning when the driver gets drowsy, but how to find a way to go with the driver to help him supporting to manage his or her vigilance through a long journey, helping him to make breaks, saying to the driver, okay, maybe you notice that it's so-so, but there impact on your driving, maybe you should rationalize that it's a good idea to really do something because you are taking risks. Okay, so that's it for today. Thank you for your attention, and I will be more than happy if you have any questions.
So thank you, Jean-Baptiste, for this very rich presentation. So are there any questions?
Hello. I have a question. First, thank you, Jean-Baptiste, for this presentation. I want to ask for the STEM project. The experiments were conducted mainly in France, or
yes, it's only in France. It's in various locations in France, mostly around Paris. It was a bit in Bretagne, Brighton, on the west of France, some in the south, but it's funded by the French government, so it's only in France. Correct.
Yeah, I'm asking that because I'm wondering if, as the project is not finished yet, are you working on this social compliance, or as you mentioned, complying with the social norms? Or are you working on minimizing this bias on the development of autonomous vehicles?
In the SAM project, there are a lot of people working on together, of course. I think the project is nicely putting together two kinds of objectives. First, for OEMs to doing some technical experimentation of vehicles, and then for people doing evaluation as me, to have some nice data to observe what is going on. So what the first point of your question, what we are doing is collecting observation from safety drivers and now from other road users to investigate this perturbation. So in some way, we include some social interaction through this incivilities question. So we are starting to that, the social processes within that. I'm really interested in digging that but we are starting from the behavior. So we are adding these layers. In the paper I mentioned in one of my slides, it was in ITS in Toulouse this year, that's our first elaboration where we try to tie together the social aspects, safety aspects. And this is why I like the Sumala model that links all these dimensions together. So this is the kind of perimeter we are working on. And then for the second point of your question, we already technically experiment in the project, getting some data to do some evaluation. It's not an ambition of the project to improve the technical functions. So we are providing our result to each OEM, and each OEM use that to improve internally the functions, but we don't really know what they do with the result. But it's not an ambition of the project at the end to say, okay, to show what has been technically improved in taking, and it takes time. So already for OEM to have the experimentation working well without safety incidents and with the given expected number of kilometers on passenger, that's already a huge job.
Yeah, for sure. Thank you for your answer.
My pleasure.
Now, Baptiste, I also have a question. So it's more like generic kind of question. So we know that humans are unpredictable, and you said it very well. Like they always change their mind. They do maybe some not conform the rules, you know, like we park where we don't have, where we are not allowed to park. We run faster than we have, and so on. But so we are trying to build this kind of intelligence vehicles. Okay, so this is the next step. I don't know when, horizon, I don't know which one. And so the idea is, do you think, what is a challenge? Because I see a challenge in the fact that building this kind of machines and vehicles, intelligent vehicles with the same behavior as humans, will not be appropriate, will not be found something that people will allow, you know, this kind of inappropriate behavior which is unpredictable, like humans, you know. So machines are more kind of, we try to make them as, I will not say as predictable as possible, but anyhow, this kind of behavior that is not going crazy, the car is doing some stupid things that like humans. So how do you think that we can deal with these both sides in order to have this kind of adaptability in the same time, but in the same time to stay to the rules, kind of? Okay,
that's a very interesting question. And I'm not saying that only because you are the organizer.
Thank you.
I think we can phrase that as a higher level negotiation. One very interesting fact in some experimentation was that people were saying that in a way, automated vehicles were pacifying the traffic flow because they are not over speeding. So sometimes it's inadequately too slow, for sure. But sometimes it makes the traffic flow more calm. So this is one side of the negotiation. The other side of there are several kind of negotiation, I think. So if we have a behavior of automated vehicle that is acceptable enough for driver, acceptable enough, then the traffic can also adapt to this new behavior, and maybe find that finally that's even better. Maybe that the first point. Secondly, the automated driving has also to reach this acceptable level for the traffic. So here there are several challenges. And one is legal challenges, crossing the lane line. That's one thing to say, okay, here I I can only think that it's rational, it's normal not to respect the rule because there is a specific situation that make it obvious. But writing explicitly in a program in the code of the automated driving that here I decide to break a legal rule is tricky. So maybe if we want to achieve this acceptability, at some point, it will be necessary to discuss with legal authorities in what are the conditions in which it's possible to break the rules, to formalize the exception, because automation does not have the ability to assess the situation and to make a decision. That could be that no one would say it's not reasonable.
And it was shown at the beginning, but I'm not sure if you were here or not. It was shown a very nice video of Professor David Serkin from Stanford.
No,
so he showed, he showed three situations, three contexts. So one in US, which is kind of, very rule-based and everything, like a normal driving on a normal streets, whatever. You had something on countryside in England, like with sheep going on the streets and the car waiting, and another one which was in Thailand, where everything was like crazy, like driving like pedestrian and like
everyone adapting to each other rather than respecting all together.
Exactly. So how do you, maybe I will say it maybe differently. This is what you said, but I'm saying also from a cultural point of view. Okay, so this is a culture coming and instead of the people like in US, like people like pedestrian and drivers are respecting themselves and they're like respecting the rules and everything. Like in Thailand, everyone it's kind of who's going first, let's say, first come first serve somehow. Okay. So how can we adapt to this? Because maybe like something that it works fine, maybe in Europe or is not going to work fine, maybe in Thailand or somewhere else. So how can we also adjust this to the cultural maybe or cultural context?
I think it's quite difficult because according to the driving culture, you are more toward the rules or more toward the each individual take care of the other. So I remember some years ago, while driving in two motorized wheels, it was in Vietnam, and that was a very strange driving experience, looking all around, but everything is going fine because everyone is extra careful. But automation is more adapted to follow rules. And when
definitely.
I can say even to reach safety, it's better to pave the way to safety by respecting rules. So here it would be a completely different paradigm, saying, okay, it's like robotic insect automations with multi-agent, okay, and ethically, it would need to accept that when something is not acceptable, that there will be fatalities that we cannot explain by a rule that was not followed or a rule that we could improve. So I think it's a totally different way of thinking of driving automation and
yeah, and I know I agree.
I'm not sure we are going toward that.
Yeah, so, I totally agree with you. But I think it's more like even country, not even cultural. Okay, cultural in general, but I think it's even to the country level that this kind of automation should be designed or not. Because I drove this summer in Naples in Italy. And it has nothing to do, it's a European country, Italy and everything, and it has nothing to do like I was driving in Paris, even if it's a very traffic or people are just like, it's completely different. So I think it's, I would say also cultural, but it's also like this kind of mutual kind of understanding of how this is working, and it's completely different from one place to another one. Okay,
Yeah,
thanks. Thank you very much.
Just a
Are
last
there
sentence.
any other questions?
Just one sentence. I do agree. I was a bit negative. We can learn locally what are the rules, and maybe we can have equipped vehicle learning while driving about the local rules. Thank you for your point.
Thank you. Are there any other question? I think we are a little bit late, but I will pass to the last presentation. So thank you, Jean-Baptiste. Very nice presentation. To the last presentation, so Shangguan is going to give a very short one just to tackle some issues and to get some insight from you. Can you stop sharing maybe the screen? Thank you, because he cannot. Shangguan, thank you for sharing your screen and start quickly the presentation.
Okay.
Thank you.
Thanks for the speakers. They all give a fantastic speech, and I will give a very short presentation. Hello, with great pleasure, I want to introduce our preliminary research about human factors using psychology questionnaire to predict driver behaviors. I'm Shangguan Zhigong, and this work has been done in collaboration with my supervisor, Adriana Dabius from Anastasia. At first, I want to invite you to watch a video with me. And this video was downloaded from the World Health Organization, as we have seen that around every 23 seconds, one person will die for road accidents. It's very horrible. According to their report in 2020, globally nearly 1.2 million people are killed and 50 million injured every year in road traffic crash, which are the leading cause of deaths among the age 15 to 29 years and rank. We can see that the deaths of the road accidents is increasing in the past 10 years, and especially we can see 93% of the world fatalities on the roads occurs in low and middle income countries, even though this country have approximately 60% of the world's vehicles. So why human factors? We want to do research in this field because from previous research, there's a general assumption that human factors involve 70 to 90% of road accidents, in 60% of cases as a main and in 95% as one of the influential factors, including inexperience, kinetic reaction, or conscious evaluation, and echo, maybe they are human factors. And human factors do matter in this kind of accidents. So our goal is want to decrease the risk on the road. So we find the most important human factors in the point of, in our opinion, that personality, driving behavior, emotion, and driving style. I want to take a little time to explain these concepts. Personality is characteristic patterns of thought, feeling, and behaviors that make a person unique. Emotion is the mental states brought on the neurophysiological changes, and style, the attitude, orientation, the way of thinking of daily driving. And nevertheless, the driving behavior, the actions of driver driving. So from these factors and the previous research, we conclude this model. The driver has a stable personality. When the driver is in a driving condition, he or she is receiving stimuli from the condition, the outside, the world, the traffic, the weather, the vehicle, the route. And these factors influence the emotion. And here is the decision-making part. This whole module might result in a particular driving style, and this part is the driver level. And on the other hand, the driving events, the acceleration, turn, lane change, brake, or throttle openness, these are driving patterns and in a vehicle level. So in conventional research, especially from the psychology research, we find the correlation between the personality or driving style, like we want the participants to write the questionnaire, fill it, and we can get a score of the personality like extroverted, optimist, neuroticism, something like this. And also use driving style self-report questionnaire to get whether you are careful, you are patient, you are distressed, or you are a high-speed driver. So it's a conventional one. For example, in this paper, personality, attitude, and risk perception as a predictor of risk driving behavior. They use the questionnaire among around 1,922 adolescents in Norway. So they can use statistical tools to calculate the correlation, even the causal inference from different factors. Like they found that the personality influence the risk perception and influence the attitude towards the safety, and eventually and at the end, all factors influence the risk in driving behavior. But this kind of research, I mean, lack of data aggregation, there are lack of the behavior prediction. Although the name of the paper is driving behavior predictor, but they didn't actually calculate how risky the driver is. So they also lack of the combination of multimodal data. So our goal is to use the personality driving data from vehicle sensors and physiological data from human beings to analyze their style patterns to better predict risk and prevent the accident in early stage. In our current research, firstly, I want to introduce our driving style and psychological data analysis. It's a data from 296 drivers from China, and they completed the driving style in winter, the Big 5 in winter, and the driver behavior questionnaire, as well as several questions about social demography information. And its data, the number of accidents fines received over the past 3 years are also recorded. And in this data, we find that normally the personality have 4 or 5 dimensions, also the driving behavior or the driving style from the view of psychology. In our data analysis, we find that in order to regard the different dimensions of personality as a whole, we use the PCA to aggregate the data. We gradually reduce the data dimension and calculate the explain the variance percentage every time we reduce the dimension of time of data. As is seen in the table, when we use 3-dimensional data, around 80 to 70% of information can be saved. Even only one dimension, 50% of the information can be saved from the original data. And if that really works, we will show our results. The right one is the original analysis. They find the correlation between the driving behavior, the personality, with the fines and the points. But they have said in the paper that they are surprised that they didn't find the correlation between accidents and the driving style. I mean, because they used too many dimensions. In our research, reduce the dimension data, we find the correlation between accidents and the driving style. Also, our correlation is more convincing. We find our correlation, the numbers are bigger than we find the correlation between accidents and the driving style. So, in addition, we use this data to make a machine learning prediction model. The prediction framework is shown in the figure. because available data sample is small, so we try to use 3 kinds of methods like Gaussian, naive Bayes, support vector machine, and random forest. And we also test the usage of the data dimension. It's the same with we have found before. When we use lower dimension data, we can get higher accuracy results. In other hand, we can see that maybe we need to compress the psychology data, and we can apply it in a data miner point of view. In the next project, I want to introduce driving style analyze and physiological data mining. In this experiment, we find 10 participants to drive on the Caroline simulation platform, and we also record their heart rate and their blink from the facial expression. This is the signals of heart rate and blink rate. We use the Kavlo filter to smooth the curve and to decrease the noise. So the result is that I will not introduce the details now. I only give the result. The result is that, as it's shown in the figure, the driver with lower neuroticism personality trait tend to blink faster, and it's a significant result. We can see in the right photo with lower. Okay, the next one is we found that the reckless and carefulness driving style driver with lower scores, they tend to blink faster. It's also a significant result. It means that it suggests that our personality and our driving style somehow has influenced our physiological behavior. Maybe in opposite, the physiological behavior influence our driving style. So it's need to be do more experiment in the future. So in the current ongoing research, multimodal analysis of psychological, physiological, and driving style data, driving behavior data is ongoing. We have 40 drivers data with 7 emotions around anger, sadness, fire, disgust, surprise, happiness, and natural. Also, we have their data of psychological, like EPQ question is kind of a personality questionnaire. Psychological data here should be a physiological data like EEG and alpha, beta, gamma, theta wave of the EEG signals. The driving behavior data like speed, acceleration, and brake. We use open face to find the feature of the facial expression. This is our first step to find the relationship between the multimodal data and the facial expressions. In facial expressions, we use the face action unit coding system to record different expression signals, like AU1 is the inner brow raiser, like AU28 is a lip suck. It means different expressions in the different part of your face. And as our first analyze, we find that in happy driving and side driving, the AU6 signals are significantly different. And in the happy driving, natural driving, side driving, and angry driving, their AU12 signals are significantly different. Yeah, it's the same with it's similar with previous paper around the emotion discovering or expression, like because cheek research and lip corner, they all turn to be upper when you are smile and be lower when you are sad or angry. So it's so they're all very interesting results. So that's all. Thank you. That's all. Is there any questions? Please feel free to ask.
So thank you, Shangguan. So this time I'm not going to ask you questions because it's our work.
Okay.
So do you have anyone else? Do you have any other questions before? Because we're past very late, but I think some questions that will be interesting to have, maybe some feedback or some questions that will be really very helpful for Shangguan to pursue this really very interesting work. No questions.
Okay, great. Everybody is hungry, I think.
Yeah, I don't know. It depends where we are.
Oh, yes.
Okay, so just to end the workshop, I'm glad that you could attend. I hope that in the future we will have maybe a face-to-face chance to meet and to have this kind of workshop in another setup, which is not going to be online. Maybe next year. So we will try to pursue and submit also a follow-up workshop of this one for the next ITSC conference, so that we can hear like the progress and to see other nice speakers, and to have maybe more like a full day and an interactive session. And like open panels and roundtable, etc. So I'm glad. I hope that you enjoyed this workshop, and I'm wishing you like a very nice Saturday for those of you who are on Saturday. And I hope we will be able to either collaborate or be able to see each other in another conference. Okay, so thank you so much, and I wish you a very nice afternoon, day, night. I'm not sure everyone, depending on the time zone. Thank you.
Thank you.
Thank you very much.
Thank you very much.
Thank you, Jean-Baptiste.
Bye. See you soon.
See you.